Welcome to another episode of The Material World. We have talked about a couple of things already. We've talked about the filamentary structures that are at play when it comes to communicating between atoms. We have talked about the necessity for material interpretation. We have talked about the reason for a continuous emission spectrum versus a line emission spectrum and the sort of material properties that give rise to that. But something that we haven't really talked about is the fundamental nature of light and the polarization of light. And is there a material explanation that makes sense for why light would be polarized? So in our model, we have a pretty clear vision of what light looks like.
Yeah, we've talked about light as being the deformation of this interatomic medium, and maybe it's not fair to call it an interatomic medium because we're essentially saying that the atoms share pieces of one another's shells. And so you basically just have this big uber atom at the end of the day, which is divided up, of course, by its subunits, which is this fiber that we're proposing. And so we've talked about light as being this deformation, right, where these atoms are putting pressure on one another across these tensile intermediary. We're saying, yeah, there seems to be a good case for there being a medium, like many people thought for hundreds of years. Except we're saying this isn't a fluid ether, like the original scientists had imagined it. It's something of a more like a tensile structure that's made out of these fibrous filamentous connections.
Which is not distinct from the atoms themselves, because when you look at something like the Michelson-Morley experiment, what you see is that they disproved the existence of an external ether through which all matter is drifting. This is fundamentally different because it is the same stuff. And so when you have light is traveling, it's a push-pull motion inside of these filaments that has a helical twist to it.
Yeah, that's what we're going to talk about today. So we do hypothesize that there's some sort of deformation, and it has some sort of directionality to it. And we know about that through this process of polarization. In general, for this reason and others, we've begun to think of light as a continual relay process. So we're going to move into all of our favorites like diffraction and refraction and reflection. You know, one of the first questions that came to my mind when I was a little kid studying light was, what the heck is happening at the level of an atom on the mirror, you know? And we couldn't get to the bottom of this for years. Actually, we were concerning ourselves with this up until, 5 years ago or something. And so we're starting to think about...
I still remember the first conversation that we had about this. I think it was in that little studio apartment in Manhattan on one of those heat wave days where we were just like barely able to move from how hot it was, and we were just lying on the floor. And we're like, well, what's bouncing around? It's like, what are the atoms actually doing? And I remember what a transformative experience it was to start thinking of light as an atomic process, as opposed to just being this like spooky photon things bouncing around that randomly impinge upon things.
Yeah, I remember we were like trying to ask your super genius little brother, like, what the mainstream physical explanation for this was. And there basically wasn't one, And so, flash forward years later.
And now we have a podcast.
Yeah, well, went and studied for many years, studied material elastic interactions and really started to realize that resonant structures imply elasticity and they apply a medium pulling this off. So to get back to the deformation itself and what sort of deformations are going on. Well, the one thing that's really interesting is that light doesn't seem to deform in a longitudinal fashion. The wave is what is said to be transverse, which means that it oscillates in two directions essentially at the same time. And so really the only structure that can pull this off is something that's twirling, something that's being twisted, or a compression wave is going through it that has like you said,
a torsion on it,
something that twists. Yeah. And so what's interesting is that the phenomena of polarization, you have a situation where an incident light can be deflected at some angle. And what you find is that there's basically two kinds of polarization. Things can either be polarized one way.
Do you mean reflected? You said deflected.
Yeah, well, deflected is probably not the right way. Relayed is probably a better way of putting it.
Sorry. I was trying to visualize and I couldn't. That's my bad.
Yeah, so it's the incident light is being reoriented in another direction.
So like it comes in, it hits the atom, and then it leaves the atom, and it's going the direction that it is going.
The impulse is being transferred to atoms in a different direction,
which is proportional to the direction at which the incident light came in.
Yeah, well, not only that, but it seems to be like you can have light that seems to be polarized in one direction versus the other, right? It can be relayed off in one way or relayed off in another. And sometimes you have something which is thought of as being relayed in a linear fashion so that it's squared up. But when you really tear that apart, you find out that a plane wave is essentially just equal portions of right and left-handed.
I am no longer following. So I'm going to stop you. Okay, so when you say that it's when it's relayed in one direction or another direction, what exactly do you mean by that?
Yeah, so if we had a longitudinal wave coming from across a series of filaments into another series of filaments, some material over here, let's say our polarizer, right? If it was just a longitudinal wave, then all the momentum would be moving in a forward direction. It could really only keep going in a forward direction. Mm-hmm. But if you have a component of that deformation which has momentum that's angled, right? We say that light has angular momentum to it, which is very interesting. Now all of a sudden when that impulse, that deformation hits the surface of the atom at the other end, it's moving in a particular direction, and that momentum can get relayed off at a new angle all of a sudden.
And so basically what you're saying is that the only light that would then go through the polarizer is the component of the angle. So what's actually happening is that helical wave hits the atoms that are in the polarizer. And the light that gets transmitted through the polarizer is only, it's this relay of the angular momentum that is headed in this forward direction. And the rest of the light is sent off in a conserved way in the direction of the rest of the angular momentum that photon had when it impinged upon the atoms of the polarizer.
I think that's a good way of looking at it, yeah. And of course, different polarizers are going to behave slightly differently because this comes down to the particular geometry of the material that comprises the polarizer at the end of the day. But the main thing that I want to take home today is just that from this phenomena of polarization, we begin to understand that light can essentially travel along these filaments with a particular handedness to it, which we call the angular momentum of the photon. And that there's basically only two options. You go one way or the other. And this is a little hard to digest because we talk about plane waves, but when you really push on the concept of a plane wave, you see that it's actually an equal mixture of both handednesses.
What is a plane wave?
It's just the third polarization that you will read about if you start studying these things in the textbook.
What's its physical qualities?
That it transmits in one direction.
And so what you're saying is that that's just a mixture of filaments that are going in, whose angular momentums are in proportion opposite to one another, and so the only component that sums is the forward motion?
Mm-hmm. Mm-hmm. Yeah, and so when you try to measure, at any point, all of these measurements of whether or not it's moving in one way or the other, they're always going to come down to an averaging of all of the gazillions of filaments that are transmitting that light in the first place.
I like that because it lets me think of the action in the filament as dissolving into the material of the atoms and then coming out the other side relative to how it came in. And so
that's what we're getting at today. I think that's really the main take-home point here. Light is a relay situation. If you want to hear more about the mathematical basis of that, check out our podcast with Carver Mead, who has essentially reworked all of the electromagnetic equations to understand light as a relay system, as a conversation between atoms. And we'll get way more into the details about that soon, particularly in terms of how you excite an atom into a new orbital shape and things like this.
We're going to have to start adding pictures at some point.
Later. We need a chalkboard or something. Anyways, we're just getting started. Leave us a comment. Tell us what we could be doing better. And tell us what other topics that you think we should get into. Because, from here, it certainly makes sense to get into diffraction, reflection, all those different light phenomena, the double slit experiment. Lots of people have been asking about that, so we'll have to do it really soon. But otherwise, stay in touch with us, and we'll see you next week.